Greetings. This is ENEE446 lecture that I missed on October 28th, 2013. And so let's get started. As I promised in an earlier audio class, I will cover encryption methods today. And so let us just start with the motivation. Encryption is an essential component of any communication or computation system that is designed with security in mind. Computer architecture design is no exception, and security has to be built into all the critical layers from the machine level to operating system and application layers of computer systems. For example, in the machine level, program counters can be encrypted to prevent people from getting a hold of the program counter content so that they can divert programs to other places that may not be, other programs that may not be as friendly. And of course, in the operating system level, system commands will have to be protected. They are so critical to secure operations of any computer system. And at the application layer itself, we have to be very careful with particularly web applications that involve internet commerce, banking, and shopping. So with those things in mind, let's just first of all look at the general idea of what we really mean by encrypting messages. So we have what's called plain text, which is something that is intelligible to an ordinary person. It could be a sentence or paragraph or a story in a given language, or it could even be some mathematical formulas or images. It could be any number of things that would be easy to grasp when, in fact, either we look at it or we read it or we hear it. Now that plain text will have to be converted, and this, by the way, can be a file, for example, a PostScript file that will just represent an image, or a JPEG file that could have image, sound, other things, or movie formats. Most all those things do have plain text representation. So I think it's safe to say that we are basically converting these intelligible messages, which we call generally plain text messages, into what's called ciphertext, which involves basically encryption or encrypted message content that makes it not so as intelligible, and therefore it needs to be deciphered, decrypted. And this whole process requires effectively a key that's much like a key that will lock and unlock a door. The keys are things that could either be privately kept, or parts of the key can actually be publicly shared. We shall see that these two ideas compete heavily in the world of encryption today. So let's just say that there are two types of encryption as a broad classification. So we have symmetric encryption, where information is encrypted and the keys are shared by all the parties completely. And once the keys are captured by an adversary, then the security system is broken, and therefore information is compromised. In the case of asymmetric encryption, we have keys that are partially shared publicly and partially kept privately. So these two principles will ultimately guide our discussion today. Now, so just a recap is that symmetric encryption uses a single private key and asymmetric encryption uses a pair of keys, one public and one private. So if we go a little deeper into symmetric encryption, a single key is used to encrypt and decrypt a plain text message. That sentence may not be exactly completely correct in that we probably have that key that encrypts the plain text message appear in some other form. It could typically be the inverse of the key that handles decryption, and there is that kind of relationship, but one can be obtained from the other. So in that regard, we can just say that there's really a single key. And so that one key that we use to take a plain text message and perhaps permute it by character is all we need to create symmetric encryption. And so essentially it's a very simple process. We just use that key to encrypt a message and then use its inverse to decrypt it. Of course, the potential con is that the keys must be kept secret, and then they cannot be communicated by public channels. They have to be privately distributed. Here's an example. By the way, these symmetric encryption methods are also known as Caesar ciphers. So a Caesar cipher is a more particular version of a symmetric encryption technique, in which encryption takes place by way of shifting the letters in a given alphabet by a certain number of positions. And all letters are subject to that same amount of a fixed amount of number of shifts, positions. So here we have an example. I guess it's a sentence that Caesar once spoke. Veni, vidi, vici is now, by way of a circular right shift, encrypted into this message. And of course, if we knew that that's what happened, that is to say, by right shifting each of these letters by one position in their English alphabet ordering, we get this particular message. We could just simply go back by taking them back in the opposite direction. So if these were obtained by right shifting these letters, then of course these would be obtained by left shifting these letters in a circular fashion. So that I guess if we're left shifting A, for example, goes to Z, and then it goes back in that direction. And the right shift, it just happens the other way around. Now this is a simple version of what we call symmetric encryption. Now, of course, it is vulnerable because since we're just talking about 26 letters in English alphabet, all that means is that the number of places, if you're just doing this shift circularly, it will be limited to 26. So you could do one shift, no shift, one shift, two shift, and 26 shifts will take you back to no shift. And so the total number of shifts will be just that. Now, therefore, you could technically try each of those 26 shifts to see if, in fact, and one of those will have to be out of question, because if you didn't shift it, that might as well be the original plain text. So even that is not the problem here. That even if in fact you did not have this problem, you could have an issue with, for example, the frequency of occurrence of these letters in a given language in plain text messages. So this table here shows that if you have the letters in the English alphabet, you can look at the, statistically speaking, of course, look at the percentages of occurrences of these letters in on the average in English text, plain text. So E, for example, is heavily used, 12.7%. It's the biggest chunk, and then T comes right after. and Z on this side is the least frequently used letter. So we could use this frequency distribution to actually more intelligently, not just randomly trying these 26 things or choices, but more intelligently looking at, for example, some ciphertext and then just decrypting this by way of looking at the frequencies of the letters, which in this case would be letter U repeated twice and then letter F repeated twice. So we can attribute those two letters then to the most frequently used letters, pair them, and they would be letter E and letter T. So we will have two choices. Either U is actually encrypted version of E, and F is that of E, and or we could say that U is the encryption of T, and F is the encryption of E. Now, once we know this fact, then we can look at this and simply figure out how much shift was applied to the original letters to actually get at these encrypted letters. So you could see that in this situation, that you could see that letter U was shifted out of T. Basically, we shifted T by one place to the right to get letter U. And the same way we get letter F by shifting E by one place to the right. So you can sort of gather by this time that, and we assume also that the shifts were constant. We'll just see that in just a second that need not be the case. But in this situation, if the fixed amount, if the number of shifts is fixed for all the letters, then we know that just shifting things back and then assigning U to, let's say, either E and then F to T, or U to T and then F to E, we could just basically carry out the rest of the shifts. So assuming that we actually make this choice, that is to say, attach U to T and then F to E, then just simply follow the course. So U becomes T, S becomes R. Just we're going back towards the left, just doing the opposite of the encryption, and then Z becomes Y, and then you can see that all of this is basically going to decode or decrypt this ciphertext into this plain text. That's how it works. Now, to make this a little harder, and we could actually not shift by fixed amounts, but by different amounts. And in general, we could just say that since we have 26 letters, we could think of a two-row matrix where the first row would be the letters in the conventional order from A to Z, and in the second row we could actually write an arbitrary permutation of those 26 letters, of which there shall be 26 factorial. So if one were to use these 26 factorial different ways of coding or encrypting the 26 letters in the English alphabet, then that number of permutations will be equal to this 4.03 10 to the 26. And so just randomly picking one of these, and let's make the assumption that it takes 1 nanosecond to make check the decrypted message to see if it means anything that is intelligible. In other words, we make the transformation from the encrypted or the ciphertext to the plain text, and then we check to see if it actually means that is useful. If that takes 1 nanosecond, then we can just simply divide the number of, and this we have to be very lucky, of course, unlucky rather, in that we really have to go all the way to the last choice. That's not very likely, but that's the worst case analysis. If that were to happen, then you would have this large number divided by 10 to the 9 seconds to do this. And that becomes let's say roughly 4 times 10 to the 17 seconds. And now you want to convert it to years, which you can do easily. It gives you this number of years, which is about 12.5 million years. So if you were unlucky and you tried each and every one of these permutations to figure out exactly what the encryption was, what the key was for the encryption, then you could really be doing this on a computer that computes each of these comparisons, and then the encryption, the decryption step in 1 nanosecond. You could spend about 12.5 million years. And this is an extreme case, so it doesn't reflect reality, but at the same time, it goes to show that even with this sort of permutation coding, you could get a good encryption technique. The real systems use a lot more complicated symmetric encryption techniques, and these are the two block ciphers that people use. DES and AES, Digital Encryption Standard, that actually preceded AES, and it's applied to 64-bit blocks and with 56-bit keys. It's called Feistel cipher, after his inventor, Feistel rather, and it takes the plain text and divides it into two blocks, and then scrambles one of them with a key, and then swaps it with the other. And then if you do this in 16 rounds, then you get your encrypted message. The process is such that you can actually go back at each step, and therefore this invertible encryption is exactly what people use to decrypt a DES block ciphered text message or plain text message. And AES is the more recent version of this. It's also called Reindl cipher. It's more complex in that it has actually byte substitutions, row shifts, column mixing, round key additions in 10, 12, or 14 rounds, and you use larger blocks, 128 blocks, and the keys are also larger. 128, 192, or 256-bit keys are used in this process. AES is the more recent of the two standards and used in commercial banking and other internet transactions. So this is really how symmetric block cipher systems are organized today. Asymmetric encryption is something that kind of departs from the concept of hiding the private keys or protecting them by way of basically, I guess you could say, just be very private about them. Well, someone in the 1970s, quite a few people, of course, but some notable people, as you will see in just a second, thought about providing a system, an encryption system, where part of the information, the key information, could be shared with between parties. Now, of course, you wouldn't do this for no purpose. You would do this because you did not want these private keys to be distributed in vaults and other physical mechanisms, because that makes that the overhead of doing that is just not too reasonable. So the idea was, if in fact one can publish, or one could publish publicly, that is, his or her key to receive messages, and that could be used in the process to send plain text messages securely. That will be a major advance, and that happened. And much of this work has happened in 1970s. And so what people do is they basically create these keys that are publicly kind of circulated, and then you use your private key to actually decrypt what is sent to you. So there's a match here. In other words, you have a lock and a key, and the key is what you have, and then the lock is what people provide to you in a way. And so you can actually, you're the one that happens to have the key that can unlock the lock that you keep in public's eye and view. So now there are two main techniques, and they actually have happened. They happen in this chronologically in that order. The first one is Diffie-Hellman-Merkle encryption, and its successor is Rivest-Shamir-Adleman encryption, RSA. And so Rivest-Shamir-Adleman kind of matches what I just described, where you literally publish your encryption key with which people can send you messages. And so you share your public key just to read messages that are sent to you in a secure way, encrypted way. Diffie-Hellman-Merkle is a little more primitive in that regard. And then there is really a process of creating what's called a shared key. So it's good to look at these in this order, these two things, because they actually tell you the progress of encryption in the asymmetric sort of sense of the word encryption. So in Diffie-Hellman-Merkle encryption, we imagine that there are two parties, Alice and Bob, and they establish a shared secret first, and then a shared secret key first, and that would be by agreeing on a large prime and a primitive root u. That would be primitive root of p, and p being prime, and u being the primitive root of it, of course, allows Alice and Bob to actually create messages by essentially having any one of the numbers between 1 and p minus 1 as their message, or any cascade or concatenation of those numbers would be a message that they may choose to send. They could send them all at once, or they could send them as discrete messages. Kind of a primitive way of, when you compare them to these block ciphers, this is a primitive process, but it nonetheless demonstrates the idea. So Alice picks a number, which will be now her private key from this point onward. That is this number A, and that's between 1 and p minus 1. And then she powers u, the primitive root, to that key of hers. And of course, she mods it to p. Everything is modded to p here. If I miss it for some reason, you have to go put it in there yourself. And sends that to Bob. This, of course, you notice that Alice is not sending A, but she's sending u raised to A mod p to Bob. So certainly, this being A being the private key of Alice, she's not compromising it in any way by sending this. Well, we just think that way, but I'll also explain this a little later. But it would have been a compromising sort of process if, in fact, she just sent it out in a public channel. People could just see A, and then she would know that that's her private key. But you could see that she's trying to conceal it somehow, and this expression, as we shall see, is more than enough to actually do that. Now, similarly, on the other side, Bob picks a number B. Again, it's between 1 and p minus 1. They could actually be even the same number. It doesn't matter. And he computes u to the b. That is, like he powers u to b, and then mods it again. And he sends it to Alice, also over a public channel. So now, the same way Alice didn't compromise by sending u raised to a mod p, her own private key, Bob didn't compromise his either, because he did the same thing here, only with this letter B, the number B. So now that they have each other's private keys in some unrecognizable form, they don't really have it. They have something, a piece of it, that they could actually use to create what's called a shared key. And they do that as follows. Alice powers what she received from Bob to A to obtain u raised to b, and that is raised to a, which basically is u raised to a times b mod p. And Bob does the same to what he received from Alice with b that he has, his own private key, and he gets u raised to a raised to b, and that is the same thing as Alice has. So now they have a shared key. They have what's called this u to the a times B mod P number. That is their shared key. That is exactly what it is. This must be mod P here again, just so that we have it complete here. Let me actually write that down, even though I said that if mod P is missing somewhere, it's like something that has to go in there. So there's your mod P. And so now let's look at what happens with an intruder. Someone who might just be eavesdropping, and that person would be Eve in this example. And Eve would like to be able to figure out what the shared key is. In fact, that would be the first thing that she will try. If she gets that, then the next thing that she may actually want to try would be to get Alice's private key and Bob's private key as well. Assuming that in fact she has one of those, it is possible that she could actually use the shared key to decode or decrypt messages on one side or both. So, but let's look at that possibility first of all. So here's what Alice does. Let's say that Alice picks her A to be 25, and then she powers the primitive root, which they choose to be 2 in this example, and then mods it to P, which is in this example 53, and then she gets this number 26. So that is what gets shipped to Bob. And Bob does the same here, except that his private key is 16, and so he powers 2 to that number, and then basically mods it to P, which is 53, and he gets 28. And then this goes to Alice. So Alice takes that number and then powers it to her own private key, modded to 53, and this is exactly this number, U raised to A times B. Again, all of this must be mod P, and that's what he computes. That is Alice, actually, she in this case computes. Let's just put that mod P in here. Let's just. It's hard sometimes to deal with Microsoft, but let's just go ahead and do that. All right, so mod P right there. And so basically this mod P gets computed here as 36, and in the meantime Bob receives Alice's public key, which is 26, and then powers it to his private key, which is 16, mods it to 53 to also get 36. Now they now have this so-called common or the shared key. Eve, on the other hand, let's say that Eve actually knows P, which is equal to 53, and she also knows the primitive root that Alice and Bob use to generate their public keys, and also their public keys primarily, and that is equal to 2. So Eve knows these 2 things. She also sees, let's say, the 2 numbers that so-called the public keys of Alice and Bob. But she cannot determine 36, that is his public key, as easily. And the reason for that is what she really sees is not enough. Like this formula here, which is really U raised to, in this situation, A mod P, is not enough to get that exponent, because this is actually called the discrete logarithm problem. If I didn't have the 53 here, then I can log this number simply to base 2 to get that number 25. The mod function creates a havoc on this powering. It's a very random distribution. This especially for large p and these, primitive roots being in some ways randomly picked, it's very, very difficult. And even if you knew that, just the shear distribution, even if you fix p and u, just looking at the distribution of these numbers when you mod a power, it's not at all how you would expect this to behave if in fact this was not here. That is to say, there was no mod. And of course it will be trivial to extract this exponent just by taking the log of this number. That not being the case, Eve struggles pretty heavily to be able to get that number 25, the same way number 16. In other words, just getting these private keys would be extremely difficult. And of course, without getting those private keys, you would like to be able to get, let's say, the shared key, which would be not 2 raised to 25 mod 53 or 2 raised to 16 mod 53, but it would be 2 raised to 25 mod 53, and then you must power this to 16 and then mod it to 53 again. Okay, and that, of course, is not the same as, for example, u raised to a plus b mod p. That, of course, if that were to be the case, you would have Alice's shared key and Bob's shared key, and then you will simply multiply them to get this. In other words, you didn't need A or B to get at the shared key. Just multiply the shared keys together. But this is not what we compute as the shared key. The shared key of Alice and Bob is equal to this, not to this. Even though it's easy to compute this from the shared keys of Alice and Bob by multiplying the two, that is not what, in fact, not shared key, I should say, the public key of Alice multiplied by public key of Bob gives you this quantity, but that's not equal to the shared key of Alice and Bob, which is equal to this. So just the sheer multiplication of the public keys will not do, is what this is saying. And you really have to have either A or B to compute this. If you had A, you could, let's say B, for example, you could take u raised to A mod p and then power it to B to get this. Or if you had actually u to the B mod p and had A on top of it, then you would actually get u raised to A times B mod p. So either A or B must be something that Eve, the intruder in this case, must possess before she would know what the shared key of the two parties in this case is. And that is as I said already, the discrete logarithm problem, and it's known to be hard to solve. Now that we understand that it is difficult for an intruder to actually get a hold of the shared key, let alone the private keys, we could kind of go onto an example of how to extract, how to actually perform message transmission in an encrypted sense. So that comes with the contribution of this man whose last name is Al-Gamal, an Egyptian, I guess, scientist. And so here's what he suggested. Alice codes her message by a number, and this is what we said earlier. There's nothing new there. Some number between 1 and p minus 1 will be her message, and that's perfectly all right. And sends the pair of numbers, which would be basically her public key, and message times the shared key between Bob and him. And so k is, of course, known to be u to the a b mod p, and this is something that Bob can compute because Bob would have u to the a mod p, and then we'll power this to b to get this number k. Now, once k is known, the rest of it is trivial, because all you have to do is multiply the message times the key, the shared key, by the inverse of the shared key to extract the message. And of course, this k is some number that is mod p. And this is a prime modulus. That means that whatever number k is, its inverse exists and it is unique. So it is computable by any of the techniques we learned earlier on. So therefore, this multiplication is not something that is difficult to perform, at least conceptually. And of course, operationally, we also showed some effective ways of doing this. So this is effectively the idea then, essentially the idea of Diffie-Hellman-Merkley encryption with Algomaal's message creation and message transmission process added in here. So, excuse me, here's an example that will probably bring these ideas home. Let's say that we pick our P to be 53, and this is an example right out of the lecture notes that I've actually emailed it in PDF format to every one of you. And our primitive root is 2. We can establish that this is a primitive root. In fact, there is a theorem that tells you exactly what these roots are in the lecture notes again. And then Bob and Alice and Bob have these numbers picked as their, as in the example, as their private keys. And now Alice wants to send 15 to Bob. That's the message, one of the numbers between 1 and 53. Alice already knows the public key of Bob, which is this number 2 to the 16 mod 53 that Bob actually shared with Alice. And he even has that, but the point is that now this number, the public key must be converted into what's called the shared key. So the shared key would be computed by taking that number and then powering it to the private key of Alice, which is 25, and then we get 36 out of this. We've already gone through this process. Having that 36 in place, we then multiply the message by 15 and mod it to 53, and that happens to be 10. Now that we've got Alice's public key, which is 26, and let's see, that is Alice's, yes, that's 26, and the 10, that is actually the encrypted message that she sends by way of this m times k mod 53 business. Bob receives this pair of numbers and then goes on to decrypting it simply by computing their shared key as 36, and that will be just what he would receive from Alice as her public key, that is 26, and then powering it to 16, and then modding it to 53. That's how actually he gets. So this shared public key is used actually once by Alice to transmit the message, and once by Bob to decrypt it. To encrypt and decrypt is the process he said that I'm referring to here. And then once Bob figures out what the shared key is, then he goes on to solve M using this equation where we have the message times the shared key modded to 53 is equated to message times the shared key modded to 53. So you can just, because this is a prime modulus, inverses exist all the way around, so you just have to multiply both sides by a 36 inverse to get at M, and that's what you do, and then you get 15, which is exactly what Alice actually had sent to Bob. So that's how the process works. As you can see, that the public key here was used by Alice to send the message, and then it was used by Bob, not the public, I'm sorry, the shared key was used by Alice to send the message, and then it was used by Bob to decrypt the message. To encrypt and decrypt, we use the shared key. Of course, we also, along with the message times shared key mod 53 or mod p, we also used We also transmitted Alice's public key, and then of course Bob used that information to form K, from which then he surmised the message by way of this algebra here. So that's just Diffie-Hellman-Merkley with Elgamal added. RSA cryptography is slightly more advanced in that the public key is really published by people who want to receive messages from others, and they just have to respect the process. That this is a known process, and that this is what they have to carry out. If someone actually had put out their RSA keys out there for people to use, they could actually be used to send messages. You just have to take your plain text and then use the algorithm that is described in here to encrypt and decrypt here. So the key generation is something that you, I guess, as the person who wants to receive messages, you pick two large primes and you call them, let's say, P and Q, and then you form their product. Now, you do this consciously, so you know what P and Q are. At this point in time, the number you formed, N, which is a product of two primes, and you could actually make it product of more than two primes, but this keeping it to 2 makes this process effective, as you will see. And now that you've got that N, that's part of your public key. You're going to use that N. In fact, just let people know what that is. However, letting what this number is, that is what N is not the same as letting what P and Q are. In fact, it is known that factoring a large number like this, and these are large primes, into two primes is not a very easy task. So therefore, it is not easy to compute this N. If in fact you pick your P and Q to be large, very, very difficult algorithms, very, very fast algorithms will have to be invented to discover what N is. And without knowing, what P and Q are. N is given obviously because whoever actually wants to receive messages, let's say Alice or Bob, will have to create this N out of P and Q. But P and Q are known to the person who actually makes his or her public key. And then once P and Q are known, then we can actually compute what's called the totient of this number N, which is by a theorem that is stated in the lecture notes, is the product of these two numbers, P minus 1 and Q minus 1. And the totient N can only be computed if you knew P and Q, because it's just this algebra right there, P minus 1 times Q minus 1. Now, once you created this, once you know what your totient function is, you want to pick a number. That is, again, what the person who wants to receive messages from anyone in public picks. So let's say it's you who wants to receive messages. You pick an integer that is relatively prime to the totient of N. Okay, and then you can compute the inverse of E mod the totient of N. Because you know what E is, you can actually compute its inverse, mod totient of N. Now, since E and totient of N are relatively prime, their greatest common divisor is equal to 1, so there is a number like D, which when you multiply with E will give you 1 mod totient of N. That is a number theoretic result, which we also kind of covered when I did some of the basic concepts in computer arithmetic. So here's what happens then. We have this number N, and we have this number E. Those two numbers constitute the public key of the person who wants to receive messages. Let's say it's Alice. It's actually Bob, it seems like, from the way I've written this, because I say using Bob's public key N comma E. That is Bob's, N and E are Bob's keys combined together. Alice uses those two keys, N and E, by way of this formula, And this is what you would do if, in fact, someone told you what their E and N values were, and then you have a message that you want to send. You would compute this C, which is M raised to E modded to N. That is the ciphertext that Alice would send to Bob by using his public keys. You notice again that N is the number that is the product of two primes that only Bob knows what they are. And of course, as an adversary, Eve or anyone else will have to have an algorithm that will know how to factor a very large number into two primes. That is the crux of this whole algorithm. It's tough to know. It's very difficult to compute P and Q. Once you compute P and Q, then you know what the totient of N is. And once you know this, and of course you already submitted to the public what E is, and once you know E, and then you have it modded to, in other words, you now want to compute the inverse of E mod a given number, that is totient of N. That's trivial. That you can always do. So just computing P and Q, like figuring out what P and Q are, this whole algorithm collapses. This whole encryption process basically is shot, becomes vulnerable, and people can actually now decipher what you're actually receiving from, let's say, Alice. So here's Bob. What Bob does, assuming that in fact nobody knows how to get P and Q, and therefore nobody knows how to compute D. D is the key here. As you see, what Bob does, as soon as he receives C, let's say, he wants to go out, he goes out and computes C raised to D mod N, which is equal to M raised to E times D. That's what C was, by the way, if you just look at it here, mod N. And that is what M is. That's all by number theory, which we'll see on the next slide. So, N and E are what Bob publishes as his own key. Alice takes N and E, takes her message, computes this, and something very similar to what Alice does is what Bob does. He takes this C, and then instead of raising it to E, he raises it to D, the inverse, and then mods it to N, and that gives you, which is this number, M raised to E times D, to obtain M. In fact, you can see this is the case in a way, because E times D is kind of like E being inverse of D would kind of wash out, but not that easily, because this is totient N inverse, this is N, but there is a fundamental relation that comes out of Euler result, that is Euler's theorem, which actually ties the quotient totient N to N. You will see this in just on the next slide. It's actually this relationship, which just is stated as Euler theorem here, which says that if you pick a number, N, and number M, such that they're relatively prime, then the totient N power of M is congruent to 1 mod N. And this is critical, because if you know this relationship, you can now go to work. You just take this fact, this relationship, and now you substitute in here. So let's say that we had Bob computing, Bob computing C raised to D mod N. Now we know that C itself is M to the E, and then we just substitute it in there, and then we put the D. Now we have M raised to E times D mod N. And of course, E times D is, since it is actually D is the inverse of E, that means their product, this product is equal to, or this product minus 1 is equal to some constant K multiplied by totient N. Remember now, E and D were inverses with respect to totient of N. And therefore that means, this D and E, if D is the inverse of E, multiplied together, minus 1 must actually be some multiple of totient of N. So that some multiple is K. And so that minus 1 becomes plus 1 because we said d times e minus 1 is a multiple of totient m. Therefore, e times d is equal to 1 plus that multiple times totient of n. And now this is where the trick comes in. So m sort of like is separated, so that's what your m here is. What is left is m raised to totient of n times k. So just take that m raised to totient of n and look at what it is. It's equal to 1 mod n. So you can replace all of this m raised to totient n mod n by 1. And that makes it go away because you power it to k, you still get a 1. So this whole term here drops out and what is left is m, and that's precisely what Bob gets. And that is the crux of this algorithm. Now Bob has what Alice sent. And this happened in such a way that Bob only sent, or not sent even, just published 2 numbers, which happen to be his RSA numbers. And anybody can use those numbers. They could be actually posted on a website. They could be there for years. Will just be there. If nobody uses them, nobody will send a message to Bob. But if anybody wants to send messages, they will pick those, that pair of numbers, and then go through this process of computing the C right there, as Alice did, to compute the ciphertext. And then Bob, all Bob does, given that it knows, and he's the only one that knows the inverse of his public number E by the totient of n, and of course nobody knows what totient of n is, because to compute totient of n, you got to have to multiply p minus 1 by q minus 1, but nobody knows what p and q are, and it's really difficult to find. If you, let's say that you want to circumvent this problem, you want to go around this problem, what exactly is totient of n? It's the number of numbers that are relatively prime to n, and n being such a large number, that will take also forever to figure out. If you wrote an algorithm to do this, it'll also take ages to compute the totient of n of a large number. This is certainly a nice formula to have, but if you don't know what p and q are, you can't compute totient of n this way, and not by brute force, not by sieve method or anything else. It'll be very, very difficult to compute this totient of n, either directly from n or by knowing or by figuring out what p and q would be. And you don't have that, of course, because like we said, factoring large numbers into their prime components is a tough problem, even in the case that you know that there are only 2 primes. Even that is difficult to do. It gives you no clear advantage as this n gets very, very large. And so Alice computes with E, and Bob computes with D. Those are the things that you have to remember. And then in both cases, one sends the message with E, the other one decodes the message with M, and thanks to Euler's theorem, which is this, and that's what makes it. And I wonder if Euler ever knew or could guess, as great a mathematician as he is, I suspect that Euler would have actually known, that someone would have used his equations, and I'm only speculating, to figure out an encryption method that is so robust. Now, of course, Euler had a lot of confidence in number theory and then made lasting contributions, like this equation alone is one of them. Even with that degree of genius and intuition, it would be hard to figure out that this RSA cryptography would be as intuitive or as explicit as it looks once we go over it. Now here I think is an example which needs to be explained a little bit, I guess, but it's in the lecture notes. So here's your prime. Here are the 2 numbers. Q. I'm sorry. These are the 2 numbers primes that you picked, and of course P and Q are there. They are. This is not the same P that we talked about in Diffie-Hellman-Merkley. Now we're picking P and Q in the sense of RSA. I got thrown off a little bit by this P in the first sentence I made. But so P and Q are the two numbers that we had to pick. Again, Bob knows these, but nobody knows what they are. And Bob also shares N, which is the product of the two, which is 901. This goes as one of the numbers of his public key. And then the totient of N is computed directly from P and Q, which will be this number, 832. So we got the totient. And and just telling us this number 832 is basically telling that there are between 100 and 900, there are 832 numbers that are actually relatively prime to number 901. That's how totient of N is supposed to be read. That's the number of numbers that are relatively prime to number N, which is 901, and that is between 1 and 100. We could say that any integer that's relatively prime to 52 and 16 will also be relatively prime to N. We want to pick that number. And that number could be picked by this property because we know that all of the factors of 832 will come from either 52's factors or 16 factors. Now, given that, and this is really all because we want to pick, if you just look back at this, we wanted to pick an integer that's relatively prime to the totient of N. So we know what the totient of N is, and that's 832, and we want to pick a prime between, relatively prime number between 1 and 900. So we're saying that, we can now examine 832, and that's a product of 52 times 16, and that's those two numbers here. So clearly there is 2 to the 4 here, and there's 2 square. So we don't want to pick anything like 2, 2 squared, 2 cubed, 2 fourth, 2 fifth. Actually 2 fifth, but 2 to the 4th. So those numbers will definitely divide 832. And so 2 will not work, 2 squared will not work, 2 cubed will not work, and so on. And then, 13, you don't want to take 13, or the power of 13 certainly will be dividing this. So what you want to do is something that is not, a 2 or the power of 2, not 13 or a power of 13, and then I guess I just say here, one number like that, it would be 3. So 3 and 832, the greatest common divisor would be just 1. So we let E, so-called the other public number of Bob, to be equal to 3. And inverse of E can be computed using this formula, which is this equation, and this formula effectively can be transformed into this formula. If you look at it, you multiply both sides by E inverse, and then E inverse becomes this number. Again, this comes from the fact that we're looking for a number that is going to be congruent to 1, and this is Euler's theorem, these two numbers are relatively prime, as this would be the case here, M and N. So M and in this situation, not N, but the totient of N will be relatively prime. If that's the case, I mean, that's how we pick the E. E is actually relatively prime to the totient of N. Therefore, M and N are replaced in this formula by E and totient of N. They are relatively prime. And therefore, like here it says M to the totient of N, it has to say M to the totient of N equals congruent to 1. It's really this same formula that we're now using with totient N, because we know that totient N and M are relatively prime. That's how we picked, M being, of course, is E in our example. That's how we picked this. We know that, as we just did that in this paragraph. We picked E to be relatively prime to 832. So this formula is valid. And then the rest of it is trivial. We just multiply both sides by E inverse, and we get this. The point of this is that now we can actually compute the inverse of E mod totient of N, and that would be what our D would be here, right there. And we compute that number here simply by doing this. That's the way to compute it. In other words, I'm just giving you a formula here to compute this thing, which is just this. If you can see, you know the totient of n, and you configure the totient of n. That means all the numbers that will be relatively prime to 832 between 1 and 831, just like we computed the totient of n the other way, the same way. And we just go to work with this. We just write d is equal to 3 raised to the totient of n, which is equal to 832. And then we use the prime factorization of 832, which is 2 to the 6 times 13. That is what this is equal to actually compute the totient of that number. Now, there is a formula in the theorem, which I think I can show you if I could actually go to this place right there. This formula, it's in lecture notes. I don't know what page this is on. Page 10, computation domain. Take a look at this formula. That's equation 5. If you look at this equation 5, it actually tells you for a number n, which is actually product of primes with their exponents, the totient is computed this way. So in our example, we only have 2 numbers in there. If you just look back here, our numbers are, it's kind of hard to see here, but it's 2 to the 6 times 13. So that basically like 2 to the 6 times 13 to the 1. E2 is 1, E1 is equal to 6. So we use this formula to compute from this, from that formula, the totient of that number 832, which is actually 382, which is roughly 2 to the 5. 2 to the 384 would be the number without the minus 1. So it's like 32 times 12. That would be 384, and then minus 1 will make it 383. And you compute this number, and then now you have to mod it to 832. All of this is simple number theory formulation, and that gives you 555. So now you have your D. And so anybody who's sending you a message, you can really figure it out by powering C to this power, and then modding it to N. That's how we said that here. Powering it to N, modding it to N, powering it to D, whatever message you get. And of course, the person who's going to send you the message will have to use N and E. The E would be 3, and N would be this number 901. So here's an example. Alice can send a message to Bob by using these 2 numbers, which we said Bob's public number they were. And the secret key, of course, is only Bob's. So if Alice wants to send a message, like message 35, whatever that really represents in her mind and Bob's mind, that 35 is, first of all, computed into what we call the cybertext. And that formula was here. M raised to E, E being 3, M being, I guess, 15. Right there. Sorry about this. Right there. That's actually 35, not 15, is what she wants to send. Raised to 3. And modded to N, N being the other public number. So you get 528. Now, Bob then computes C to the D, which this number 528. D we just computed to be 555 here. Power to that, and then mod it to 901, and you get 35. And that's the message that Alice sent. And all these extremely large numbers, actually very small numbers, but even in our situation, like powering 8 to 555 is quite a powering. But the way you simplify this is you could actually do recursive powering, as I covered it in my earlier audio class. Some of this can be simplified. So all this number crunching can actually be turned into effective processes, even when these numbers become much, much, much larger. And they are. In the real world, the n is not 901. It's into trillions of a number. And so that's how you make these things extremely difficult to decipher. So I guess this completes my discussion of encryption. And I will now bring this to an end. And I will actually email this to, I will upload this first of all to my website. And then I'll email you the link so that you can download it and then maybe use it as part of your learning process. I hope that this will be helpful in some ways. But if you find this to be not very helpful, or if you have further questions as a consequence of this discussion today, please do send me an email, and I'll be happy to do my best to help you with this. So until our next class on Monday, everybody take care, and I'll see you at 2 o'clock on Monday. Of course, I will also try to audio record our Wednesday class so that those of you who want to actually get going to get reunited with your families, parents, can do so at the earliest time possible on Wednesday. I'm very much looking forward to facilitating to you so that you'll have a happy reunion, and I'll be back completely re-energized by Monday after next. Okay, so I'll see you in class, and for right now, I just say goodbye.